Hello, this is Jack Jackson. In this video, we're going to look at some similarity transformations using matrices. So, including dilations along with the isometries and then all the compositions of those things generates the group of similarity transformations. Similarity transformations include all the isometries, dilations, and all products compositions generated by these transformations. These do not generally preserve congruence or distance, but they do preserve betweenness, linearity, and angle measure. Most importantly, they are linear transformations which preserve similarity. A dilation by a factor of alpha greater than 0 results in multiplying all lengths by alpha. It results in multiplying all areas by alpha squared, but it leaves angle measures exactly the same. The following table gives the matrix representations. So for a dilation using a two-column matrix, you can multiply by the matrix alpha 0, 0, alpha. Or just do a scalar multiple by alpha. So scalar multiplication is a dilation in the vector space structure here. I'm not going to bother filling this one in because I don't really care about it as much. I'm more interested in the three-column versions. So notice if you take this two-column version here and then have 0, 0, 1, of course always 0, 0, 1 on the bottom, but have it on the column as well, that gives you the matrix for a dilation. You can verify that if you multiply this by point xy, or the xy1, the matrix for that point, that you will get alpha times x and alpha times y, which is a size transformation dilation centered at the origin. And I'll show you in just a second how I got this one down here, but this is the more general dilation about a center point hk and by a factor alpha. So we can put these in the TI Inspire, program them in just like the others. Dilate O for the origin, dilate about the origin. I'll use A instead of alpha. A00, 0A0, 001. Store that as dilate O of A. And to get this more general one up here, here's what we're going to do. We're first going to translate by the vector minus HK, which is going to basically move the entire plane down to where that center point is no longer at HK but at the origin. Then dilate about the origin by alpha, and then translate back by HK. If you think about the geometry of what's going on there, that should make sense that that gives you a dilation about HK by factor A. And if you multiply those matrices out together and then store that as just dilate HKA, it runs off the screen here, but it looks like this at the end. It'll say done, and now if you pull up that command and just put in HKA, you'll get this right here, which is equivalent to what we have up here. I just factored it out. Okay, and so that's how we get a general dilation. So let's try this here as an exercise. Okay, first try to do it without a calculator. Use matrices to perform a dilation of factor 2 about the origin on a triangle with vertices 0, 0, 0, 4, and 3, 4. Then use the TI Inspire to check your work, and then finally check it geometrically with GeoGebra. What's the ratio of the area of the resulting figure to the original area? See if you can figure that out on your own. If you have your TI Inspire with this programmed in, go ahead and take time to make sure you've done that, and then use it, get GeoGebra up, do all that stuff. Do it on your own, come back and check your work in a minute. Press pause now. All right, you're back, so hopefully you've done this yourself. The matrix is going to be 2, 0, 0, 0, 2, 0, 0, 0, 1. We're going to multiply that by the point matrix. X coordinates are 0, 0, 3, Y's are 0, 4, 4, and you always have 1, 1, 1 at the bottom. And if you multiply this out by hand, you're going to get this this set of matrices, this matrix right here, which says that 0, 0, 0 is going to stay 0, 0. Of course, the origin's a fixed point since it's the center of the dilation. 0, 2 is going to go to 0, 8. And I'm sorry, 0, 4 is going to go to 0, 8. Okay. And 3, 4 is going to go to 6, 8. What you really end up doing is just multiplying both coordinates by alpha, which should certainly be easy enough to do by hand rather than using a calculator. Maybe that's a little bit overkill. But nevertheless, we're trying to see how to do this. But you could do it this way, dilate dilateo, which you can type in, or you could just pull that function from by hitting the VARS key, and you'll see it in your list on the TI Inspire. Enter in the 2 there in the parentheses and our matrix here for our point matrix, and you'll get the image matrix over here. The interior, well, all lengths, distances from the origin have been doubled, and all lengths have been doubled, so distances from the x and the y-axes have been doubled, so all coordinates have been doubled. If you had other things related to this triangle, like that are links, like an altitude or something like that, it would be doubled as well in the image. But area is so since both base and height have been doubled, then the area is going to be multiplied by that alpha or that a squared. So 2 squared is 4, so it's going to be 4 times the area. Here's the picture of the original one, and everything's this one stays where it is. This one goes out in a line here, but twice as far out. This one goes out in a line twice as far out to here. That agrees with what we had there. And we see the area is 4 times as much. We could actually decompose this into some congruent figures. If you'll take this right here, from right here straight down, that makes a triangle congruent to this one. And if you'll connect B and C, then we'll have 2 other triangles congruent to that. You have 1, 2, 3, 4 triangles there that are all congruent 4 times the area. So now we have, not only do we have functions for making matrices for all of the isometries, we have one for dilations as well, one for dilation about the origin, another one for general dilation. And now we can use that in combination to get any similarity transformation.